future of this. I guess we want to get started right off the hop with, let me just make sure I'm on the right one. Yeah,
Okay.
I guess the mission architecture as a whole. Go.
Yeah, okay. So, yeah, China has been gradually building up its space program for a long time. And then in the early years of this century, they started planning for a lunar exploration program, and they have been remarkably successful. Now, one thing I would say that if anybody's interested in space and they've been watching the news over the last couple of years or so, they've seen several stories of spacecraft that crashed on the moon and didn't function properly, right? China has landed 3 things on the moon now, and they've succeeded every time. So, and they have another one coming up in only a few weeks. So they've had a very successful program. So let's have a look at it. What the plan was to gradually, let's stay with this one. The plan is that first you're going to send something to just orbit around the moon, and it can take images of the surface, and it can make other measurements and so on, but mapping the surface in different ways. So they were going to do that. Then they wanted to land, and the lander would have a rover, so they'd be learning to use a rover on the moon. And then they wanted to do a sample return, to scoop up samples and bring them back. But they had never done this before when they started out. So for every one of those steps, they had 2 spacecraft. In case if the first one fails, then you've got a backup and you can go, fairly quickly with that. But actually, every one succeeded. So in that case, the backup spacecraft could be maybe improved a little bit and used for something additional to what it would have done otherwise. So they've had an extremely successful program. So let's move ahead. The first one was Chang'e 1. And that's an orbiter launched in 2007.
Okay,
Now, its goal is to map the moon. And of course, you might say, well, hasn't the moon been mapped already? True, it has. But 2007, which is before NASA's Lunar Reconnaissance Orbiter, what had been mapped was still pretty patchy. And also, of course, the Chinese wanted to actually learn how to do this and get their own data sets and learn how to work with them and everything. So it's not enough to just rely on other people. They wanted to do it themselves and learn how to do it in the process. So they go into orbit. They've got stereo cameras for photographing the surface, a laser altimeter for mapping topography. That top map there is topography. And the middle one is the imaging data set, although of course much more detailed than what we see there. And they had spectrometers to measure composition, and this microwave radiometer thing that gives you the temperature of the surface, but also tells you something about the depth of the regolith, the lunar soil and stuff like that. So a bunch of instruments, and it was very successful. It mapped the moon in all those different ways, and some of them are things that had been done before, although they were done a bit better here, and some of them had not been done. So that microwave radiometer is unique and hasn't been flown on any other kind of spacecraft. So it gives good information about the structure of the regolith all over the moon. Okay, and then at the end of its mission, it was commanded to crash on the surface in March of 2009. So let's have a look at the next slide. Yeah.
I was going to say on this one too, like I'm often, I guess when you're talking about the solar system as a whole, sometimes you brush over Mercury and the moon in a sense of, they're not that dynamic compared to some other things, but that bottom temperature map at least gives you some sense of like, okay, the moon's not nothing. It's not one dead cold rock necessarily. There is some dynamism to an extent.
Yeah. Yeah, that's right. Okay, so Chang'e 1 was commanded to crash on the surface, and naturally, the Chinese had a prediction for where it would be. But the question is then, a question is always for me anyway, can we actually find the exact location and study the impact feature that it made? So this is another case like that Apollo 16 one we just mentioned, where it was possible to go and find the impact site by looking through a lot of pictures. Now the trouble is, what are you looking for? Is it going to be a regular crater, or is it going to look different in some way? And what I already said about the Apollo 16 lunar module ascent stage impact applies here too. It's not a typical crater. And when it sprays ejecta out, it's mostly going downrange, kind of ahead of the impacting spacecraft. But when I was looking for this, I didn't really know exactly what to look for. So I'm looking at modern images, the Lunar Reconnaissance Orbiter images, and every now and then you find a funny looking crater. You know, it's a little bit of a funny shape, or maybe it's got dark ejecta instead of bright ejecta or something like that. There's something that looks a little bit funny about it. And I had 3 or 4 of these kind of candidate things in the right area, and any one of them could have been the impact, but how can you tell? And then I figured out that actually that area had been photographed before, and in fact by Apollo 16. So I was able to go and find the Apollo 16 high resolution image of that area and compare it with the modern Lunar Reconnaissance Orbiter image. And as I flipped back and forth between them, all the things that I thought were candidates turned out to have been there years before in the Apollo 16 image. So they were wrong. They were old features, not new features. But as I was flipping back and forth like that, I noticed this little thing kind of flickering on and off. It's off when I'm looking at the old image, and it's on when I'm looking at the new image. So it's a new feature. And that turned out to be the impact site, and it has all the characteristics I'd expect. You can see on that sort of lower right-hand corner, it's like a bright fan. It seems to be coming out of a crater, but that crater is not the impact site. That crater was where the spacecraft crashed into the surface, and it basically nicked one rim of it and then splattered across the crater and hit the other rim and sprayed out in a cloud of ejecta. As I say, that feature was not there in Apollo 16 images, so it's new, and that must be the Chang'e 1 impact site. Is very close to the predicted point. So that's a little bit of a story of how you find something like that.
Yeah, these are all LRO images that we're looking at?
Yeah, these are, yeah.
Right, yeah. So then it must be quite a bit of work to get the Apollo 16 images to a place where you can flip back and forth.
Yes,
They're not
it
at
is.
the same angle. They're not at the same resolution.
No, that's right. It is a lot of work. It takes quite a bit of doing, but you know, it can be done. And when you get it set up and the images are registered so they line up on top of each other perfectly, then it becomes quite obvious what
that's the easy
what
part.
you're looking for. Yeah, that's right.
Yeah, that's comparatively easier than lining them up in the first place, I would think.
And I should say that this idea of comparing a previous image and a later one, 2 images taken at different times, and flicking back and forth to look for something that's changed, that's exactly the way that the planet Pluto was discovered. Way back in 1930 by Clyde Tombaugh, comparing images of the same bit of the sky taken at different times, and something had moved, and it was Pluto, and that's how it was discovered. So this is a strategy that actually has a long history in astronomy. All right.
Nope, that's wrong.
So that was our first orbiter. And now here's Chang'e 2. So then they flew the backup orbiter. This time it had a better camera. It took much higher resolution images of the whole surface of the moon. That was so they could search for landing sites for their future landers. That's just an example of one of their images. And after they'd finished mapping the moon, it was sent off to orbit around a different point in space, a Lagrangian point. And then it was released from that to go and fly past an asteroid. So quite a productive spacecraft. Right now, it's in orbit around the sun, but it will eventually come back to Earth, maybe in the 2030s. It's conceivable that they could contact it again. We don't know if it will still be working. But quite a productive mission.
Titatis is an asteroid you know well, Phil.
It is, that's right. Because it was intensively studied using Earth-based radar images we used to make a shape model of it and map it and so on. And there's quite a literature on that. But the radar image model had never been tested by looking at the thing close up. And this is the first time that any radar imaged asteroid had been seen close up like that to do a detailed comparison. There were cases where we'd had low resolution radar images that don't really tell you very much. except the overall shape. And then we got spacecraft images. But this is the first one where we had these really detailed radar images and camera images, and we could compare them and basically prove that the radar mapping work was giving reliable results.
Is that one you did?
I did make a shape model of Tutatis and a map. It's out there somewhere.
Yeah, maybe I'm misremembering, but I remember when one of the assignments for your course was to find the first map of each mapped planetary body.
Yeah, yes.
And there were a few in there that were you.
Yeah, that's true.
Them.
That's right. Yeah, this was one. Yeah. Okay, so now let's come to the first lander. Chang'e 3 launched in 2013. So the goal was to land on the moon, and this was the first time since 1976 that anything had landed on the moon. There'd been a long gap there. And it released a rover, which worked for just a couple of days. And in the second lunar day, it suffered a fault. It still gave some interesting results, though, while it was driving around. So I don't want to put it down too much. The lander is actually still alive now, more than 10 years later. But as far as I can tell, it isn't actually doing anything. It's just that every now and then they're able to communicate with it. So it demonstrates that it's survived. Let's go to the next slide here. This is just a little bit about where it landed. So first, you have to have good photography of the landing site. And the Chinese were able to use NASA's Lunar Reconnaissance Orbiter images, which are available to anybody. But they also took their own images with Chang'e 2. And the top map at the top shows a kind of a box, which was their landing area, and their image coverage across that box at particularly high resolution to help with the mapping. And then below it, there's a sort of a geological map. Basically, there were old and young lava flows here, and they landed close to a boundary between them with the hope that the rover might survive long enough to be able to analyze both of those sets of lava flows. But in practice, it didn't go far enough to do that.
Relatively close to the first rover ever.
This was it was well, there were Soviet rovers in the 1970s.
Yeah, that's true. Lunar 1.
Yeah, Lunar 1 and Lunar 2. That's right. So there were Soviet rovers. This wasn't the first rover ever, but it was the first rover in modern times, shall we say.
No, I mean, they landed close to the first rover ever.
Oh, I'm sorry. I'm sorry. I should have. Yes, you're right.
Yeah.
They did. Not too far away. That's right. Yeah, about 300 kilometers away. And here's a little close-up at the landing site, showing the path. It came off the north side of the lander, and it looped around and went down to the south side, and looped around, and it went to look at a big rock, and then it came back very close to the lander, and then it failed. But it was going to bypass the lander and go and analyze some rocks at the top of this image, and then go on a drive that would eventually take it close to that other lava flow, where they might be able to analyze a different kind of rock. They didn't succeed with that, but they did get quite a lot of analyses of the composition of the soil and rocks where they were. And they used a ground-penetrating radar to map under the surface, which is the first time that had ever been done on the moon. Infrared compositional data and stuff like that. So it was actually quite a nice, productive little rover. Okay, that's oh, and yeah, this just shows a nice picture of a big rock at the bottom there, and a little bit about the landing site with some names that the Chinese gave to assigned to those craters and to the landing site itself. The Chinese have been quite keen on landing things around, on naming things around their landing sites, and it remains to be seen whether other people will do that. But the Chinese are quite keen on it, so they give a lot of names to features. And the lander had a telescope on it, which is operated for a few years. Yeah, so okay. Now, that landing succeeded, even though the rover wasn't terribly successful. But the second rover, they decided to do something much more difficult and challenging with that and land it on the far side of the moon. The first time anything had ever landed on the far side of the moon. And if you're going to do that, you need a relay, a communication relay. And that's what this spacecraft was. I hesitate to try to pronounce this. I think it's something like Chao.
Yeah.
Even, yes. So anyway, it was put into orbit around a point behind the moon, a Lagrangian point, where it could go in a long, slow looping orbit around that point. And from the Earth, it would always be visible kind of out, beyond the moon. It is circling around the moon as seen from Earth. So it's always visible, but it can also see the far side, so it can relay communications. The name means Magpie Bridge, which comes from a Chinese astronomical legend. And it was very successful. The bottom image there is taken from a little spacecraft called Longjiang 2, which flew alongside Chao here. It was supposed to operate with a second little spacecraft, but the second one failed. So the first one just took some images and so on, and eventually it crashed on the moon as well. And we found that site too, although I didn't find it. Okay, let's go on to the next one there. So now we come to Chang'e 4. And this is the second lander, then the backup lander that sent on a more challenging mission to the far side. Landed at the beginning of 2019. Still operating 5 years later. This little rover is called U-22. And the lander, we can see in that image there, has a big antenna sticking up, and there's also another one coming out this left-hand side, and a third one that we can't see here. And they're for a radio astronomy experiment. So these things are doing all sorts of experiments, not just driving a rover around. They're doing radio astronomy, and the first lander for Chang'e 3 had an ultraviolet telescope on it, so they're interested in doing some astronomical work as well. Okay, let's move on. The next slide there. Yeah, so where's it going to go? Well, what they wanted to do, they decided to send it to a place where that white arrow is pointing in the upper image. It's in the mid-latitudes in the southern hemisphere, but it's inside a great big depression, and that big blue and purple patch at the bottom is a big depression, and we call it the South Pole Aitken Basin. It extends all the way from the South Pole at the bottom up to a crater called Aitken at the top edge of that circular patch. And not too far from the middle of it is where Chang'e 4 landed. And the lower map just shows that landing site on the right-hand side. It's inside a crater called von Karman, and it's got a very flat floor covered with lava flows. But in this particular area, the lava flows are covered over with ejecta, stuff that's been thrown out of a nearby crater. So they're not looking at the lava right now, but they would like to drive far enough that they can actually reach some of this lava. So that's what they're trying to do right now. Okay, so let's move on. Here's a kind of a little map that shows the path that the rover has followed. There's a white line, the star is the landing site, and the white line shows where they've gone. This makes it look like a rather mountainous terrain, but this is grotesquely exaggerating the relief. The blue and green bits are low, and the pink and white bits are high. But there's not very much difference between them, maybe sort of, say, 10 meters over the distance of a kilometer, something like that. So these are very shallow depressions. Even so, it's an undulating surface, and actually much more of an obstacle than those shallow depressions is the fact that it's just covered with all these craters. So you have a very windy path, and they can't drive very far at a time. What they do is they get to a certain point, they take photographs all around them so that they get they can make a little stereo map of their surroundings just out about 10 meters or so from the rover, and then they plot a safe path through it. They do that drive, and then they have to repeat that process. So they don't really get very many drives in a lunar day. Often it's only one of those drives in an Earth day, and they only get to do that about 6 times during the course of a lunar day. because of some temperature limits and things like that. So anyway, it's because of that, it's not going very long distances. The total distance it's gone is only about 1,600 meters in 5 years. And to put that into perspective, our rovers on Mars can drive twice that in a single. Oh no, I was going to say in a single drive. I better correct myself there. The Soviet lunar rover, Lunar 2, on the moon in 1973 drove twice that distance in 1 day, 1 terrestrial day. So it's going slowly, but it's doing lots of good stuff along the way with ground penetrating radar, mapping the subsurface, analysis of rocks and that kind of thing. So it's been a good mission, a productive mission. Let's move on. Yeah, here's just a little bit of a path map, just for a small part at the beginning of the mission. But it shows basically where they stopped at each night. In the first couple of days, they drove quite a few times during a lunar day, but later on they kind of reduced that to just a few drives in the lunar day. But you know, they had lots of opportunities to map things and analyze things. I've got a white circle there, which is a buried crater detected by that ground penetrating radar. So yeah, let's go on now. And just a few typical pictures. There's a kind of a little crater with a gravelly rim that they analyzed at one point. In the lower left, you can see a beautiful little glass ball. That was something, that's rock that was melted by the heat of a large impact and thrown out. And as it flew through the vacuum of space until it hit the surface, it cooled and solidified into a beautiful little glass ball. And then it sat there until the rover came along and photographed it. And the Apollo astronauts picked up 1 or 2 of those as well. Yeah, so it's done lots of interesting stuff. Let's just move on to the next slide here. This is the ground penetrating radar, what it looks like. This is just about 1,000 meters of its path, and it's done more than that now. But you can see that you're able to look down through multiple layers of stuff. And you know, they're getting a sense of how different layers of crater ejecta have piled up on top of each other, where there are buried rocks. Ultimately, if it goes deep enough, they could see where the lava flows underneath it are. So this is good geological information. This is the first time this has been done on the moon, this and the previous Chinese rover. But the Mars rovers are doing this now with very good results. Okay, and there's a little picture of the lander, Chang'e 4 lander, from a distance, with the rim of the big crater it landed in behind it. Quite a beautiful landscape, I think. And what they're trying to do now is to reach this area where there are lava flows. And the first sign of them might not be that they're on the lava flows themselves, but that they find a rock that's been thrown out by a crater that hit the lava flows, throws the rock out, and they find that rock. So every time they find an interesting looking rock, they do an analysis of it to see if they're picking up something that's come in that direction. But they haven't found one yet, as far as I know, and as far as the publications are telling us right now. They haven't found that, but that is the goal.
How is the like, compared to keeping up with the Mars rovers, how is it to keep up with Chang'e 4?
Oh, it's tricky. In the earlier part of the mission, really for about the first 3 years of the 5 years it's been operating, every month we got a nice little sort of blog post called the Drive Diary, which outlined what they had done in a particular lunar day, with photos and maps and so on. It was really quite useful. But they stopped doing that a while ago. So now we just rely on intermittent reports and published maps.
And of course, not to go off on a tangent, but last week was LPSC, where there's some Chang'e 4 presentations.
Yes, they were, and the most important one, I think, was of the ground penetrating radar mapping a longer section than the one that I showed there.
Cool.
So, yeah, that's right. Okay, so now the next thing is that the third step in the Chinese lunar program was going to be Chang'e 5, a sample return mission. And people counting craters on the lava flows thought that it was going to be the youngest lava flows that had been visited yet. So let's go to the next one here. Have a look quickly at this. There's the return spacecraft on the ground after they got it back, and some pictures that they took along the way. So they made it work. Now, the thing is, if you're going to bring something back from the moon like that, it would be really nice if you could test it first. And so they flew a test mission called Chang'e 5 T1, the first test for Chang'e 5, which carried a sample capsule, but it didn't land on the moon and collect a sample. It just looped around and came back. But they tested that it would survive the re-entry into the atmosphere. And they took a few photos as well. Let's move on there now. Move on to the next one. So here's Chang'e 5 itself, and some dates there. Launched in November 2020, landed on the 1st of December. Was only on the moon for 2 days, the sampling part of this anyway. And on the 16th of December, it returned to Earth. Very successful. There's just a couple of pictures. The first one shows the spacecraft leaving its orbiter, and the second one shows the return part of the spacecraft blasting off from the lander. Okay, let's move on. And this shows what they did. So there's a little sampling area up at the top with the sampling arm. There are 2 different ways of collecting a sample. They drilled down into the surface and got about a 1 meter long core of surface material. And they used a scoop on an arm. It would scoop up and then put that in the return capsule, scoop up some more, put that in the return capsule, and so on until it was full. That's what they did. We can see the scoop marks there. They scooped 12 times to scoop that stuff up. There's a photo of the landing site with a distant mountain on the horizon there, and a kind of a fisheye effect image. But very successful. And the samples turned out to be about 2 billion years old, which is very young for lunar lava flows. So there's been a lot of excitement about the results all over the world. The Chinese had access to the samples first, but now anybody can apply to use them.
So clarifying that, because moon, give or take, 4 billion years old. Right. So we're about halfway its age, but in terms of things we can get at, that's young.
Well, yeah, if you look up at the moon, you can go out and look at the full moon and you see bright areas and dark areas. The bright areas are about 4 billion years old, and the dark areas are about 3 billion years old, give or take. Okay. But this is from the last, kind of one of the later stages of volcanic activity, about 2 billion years ago. There might be 1 or 2 other places on the moon where there are also young rocks, or even slightly younger than this. But this is the youngest that we have so far like this.
And then that timeline implies that for roughly the last 1 to 1.5 billion, the moon has been very similar to what it is today.
Yes, that's right. Very little change, except for some enigmatic features that we're still puzzling about. But
sure,
yes, but by and large, nothing much has changed. All right, and this is just a little map of the landing site and the diagram of the spacecraft itself. We can see a kind of a jagged outline on the left, a sort of butterfly-shaped outline, which is mapped with an infrared spectrometer. So the first thing they did was to take those infrared images that give us some composition information to look for things that, any special thing that might be of interest in that area. It's actually relatively uniform over such a small area. But anyway, let them choose a site to sample, in fact, several sites. And then the sample arm, which could go anywhere in that kind of white arc, could be directed to the places that they wanted to sample. And that's, so there's some planning involved in doing this kind of thing. And this is just a little diagram showing step by step the 12 scoops that they made. This is one of the things I like doing, is making sort of little step-by-step illustrations that show the progress of activities like this. And one of the things you noticed, this came from a paper about the sampling process. I put the composite together, but the individual images came from this paper about the sampling process. And one of the things you could see as you go through them is that sometimes there would be a little rock on the surface, and that's where the next scoop was made. They're trying to get that little rock in the sample, and they probably succeeded sometimes, but I haven't seen a detailed analysis of that. Okay. Well, okay, so now the first sample return mission then landed on the Earth-facing side of the moon, but they decided that its backup, the next one, Chang'e 6, which will go to space a month from now, it should go to the far side of the moon and be the first sample return from the far side of the moon. But that means that you need a computer relay, I mean a communication relay, sorry. So the old Chang'e spacecraft was malfunctioning. It's not very easy to operate anymore. It's very, very low on maneuvering fuel, but it needs that to keep a stable orbit. So they're trying to minimize the use. It's been very tricky to use anyway. So the little Chang'e 4 rover has been very restricted in what it could do over at least the last year because its communication relay wasn't reliable. And it certainly was not reliable enough for this new sample return mission. So a new relay, Chang'e 2, as it was launched just a month ago and is now in lunar orbit, along with two little experimental satellites that are also there testing systems for future relays. So they're on station and just getting themselves set up so that everything's ready for the new sample return mission. And then they'll also be able to make the Chang'e 4 spacecraft and its rover more productive again. So let's look ahead. So now we have to look into the future a bit, starting with this Chang'e 6 mission. It's going to launch in a month and try to collect samples from the far side. So these will be the first samples from the far side, and only the second far side landing. The Chang'e 4 and Chang'e 6 will be the only things that have ever landed on the far side, although there are plans for future landers on the far side later on. Anyway, this is what they want to do. Let's have a look at the landing site here. So the top map shows where they go. It's inside that big South Pole Aitken basin again that we saw in a previous map. Not too far away from Chang'e 4, but in a different kind of place. There's a great big circular impact feature called Apollo inside the South Pole Aitken basin. And they are going to land near its rim. They designated 3 areas that you can see in the bottom image. They seem, at LPSC this year, they seem to be most interested in the one called F there, flat plain, which is a lava flow that also has some stuff on it thrown out from a nearby crater. And that stuff, that ejector from the other crater, will be the stuff from the floor of the Apollo impact structure. So they'll be getting samples of both of those things mixed together. And there'll be a lot of very interesting information in those mixed samples.
That's going to be confusing. Like
no, it's not.
Paper in the future will say like Apollo samples.
No, it's not. Well, I know what you mean. Yeah, I understand that, but I think they'll probably find productive ways to avoid that confusion. But yeah, obviously that could be an issue if you weren't careful. But it should be very interesting anyway. And then Chang'e 7. Now, so the initial program of 2 orbiters, 2 landers, 2 sample returns, that's ended with Chang'e 6. But China has decided to extend that with several more missions. So Chang'e 7 will fly in about 2026 and go to the South Pole. And they have a site picked out that they're interested in. It's going to have a rover to drive around. It'll do analysis. They're going to have a hopping spacecraft that they want to hop into a permanent shadow area, do some quick analysis, and then hop out and maybe hop again somewhere else. This is quite a popular idea. There's another one, that, an American one like that will fly at the end of this year from a company called Intuitive Machines. So anyway, this will go to this very southerly, hopefully volatile rich site, that is lots of ice and other frozen stuff like carbon dioxide and so on. And they can hopefully analyze some of that frozen stuff as well as the rocks that we're used to seeing. Yeah, so that's Chang'e 7. And Chang'e 8, and here I can see I have made a mistake. So Chang'e 8 should be in 2028, and I haven't corrected that. So let me correct that verbally right now. Chang'e 8 in 2028 will go to the South Pole, but the site hasn't been chosen. The image there is from a presentation a few months ago that shows areas they're thinking of, but basically we don't know exactly where it will be. But somewhere in the far south, and this is going to be testing our ability to actually do things with these surface materials, especially ice. If you can recover ice and get water from it, and maybe get other substances from it as well, what can you do with it? You know, can we design the equipment that would extract water from these frozen ice reserves and you know, do something with it? So they're going to be testing things like that, a process that's called in situ resource utilization. And that's what they're going to experiment with on Chang'e 8. And if we go to the next slide, they're going to follow that up with something that they call the International Lunar Research Station. So this is a joint effort with China and Russia, although China is very much the senior partner in that, with the biggest parts of it. And they have other participants from around the world as well. But the idea is that you're landing robotic spacecraft and you're building up infrastructure, and there'll be rovers going around doing things and maybe tending to and constructing some of the infrastructure and all this sort of thing. And eventually humans can also visit that site. And this is actually very similar to another notion in Europe called the Moon Village, which would be exactly the same setup. It perhaps is also similar to what NASA is thinking about for the future, after a few human landings, building up something called the Artemis Base Camp, which again sees a buildup of infrastructure and humans visiting it on a fairly regular basis. So this is the direction that things are going in China and in Europe and with NASA. And Canada will certainly be along for the ride with the American one.
So with the forthcoming ones, they're all focused on the South Pole for the most part, it seems.
Yeah, they are. That's right.
And the ice is the driver there.
Yeah.
Yeah. Okay. So are they foregoing anything particularly interesting elsewhere? I'm trying to think.
Well, what the way things are looking at the moment, those other sites will be visited robotically, but there's nothing in the Artemis structure that wouldn't allow them to send people to another site of extreme interest on some other occasion. So that might still happen.
Okay. Cool. So yeah. 6 is going to be launched next month.
Yeah, early May. That's right. So just about a month from now. And it's a mission that will last about a month and a half. So there'll be quite a lot to follow along the way as it flies.